Hope you're having a good day. Today I'll be discussing an introduction to nonlinear optics and wave mixing. And to do this, we need to understand the concept of polarization and how it can be expanded into linear and nonlinear terms. So in previous videos, I've talked about polarization. Sometimes it's called a dielectric polarization or induced polarization. And it's the response of a material to an applied electric field. So, for example, imagine you have a material that's neutral, okay? Even though it's overall neutral, it's still made up of positive and minus charges, like this. And they're randomly oriented. So this doesn't seem very random, but it's random, so it's overall neutral. Okay, so this is a neutral material. We're going to take this material, and then now let's put this material in the presence of an E field. So this is at some time where we're not applying the field, and this is at another time where we apply a field. And let's say the E field is pointing up. So if the E field's pointing up, all the positive charges are going to want to move up in the direction of the arrow. All the minus charges are going to move in the opposite direction. So our material is going to become polarized like this. Okay, so the polarization is going to oppose the electric field. So most of the time, the material polarizes linearly, or in other words, if we apply an electric field of 1 unit, the polarization, the material is going to be polarized 1 unit. And if we increase that electric field by 1 more unit, well, then the polarization increases by 1 more unit. In other words, the derivative of the electric field with respect to the polarization is a constant. So most of the time, the material polarizes linearly, and that's described by the polarization P is equal to epsilon naught times chi. Chi is the susceptibility, the electric susceptibility, times the applied electric field. So P is the polarization, and that's the response of the material to the applied electric field. This is the applied electric field. This chi is the electric susceptibility, and this epsilon naught, it's sort of the electric susceptibility of the vacuum. So some people refer to it as the vacuum susceptibility. I think it's susceptibility. I always get the magnetic and the electric one confused. But anyways, the important thing is epsilon naught is a universal constant. It doesn't depend on the material, whereas chi depends on the material. So in previous videos, I've also talked about these concepts in a sort of microscopic point of view. And so from the microscopic point of view, so this is more of a macroscopic point of view. In a microscopic point of view, the polarization is analogous to the dipole moment mu. And, in case we want to be super strict, the polarization is a vector, so is the electric field. Dipole moment's a vector, and in the micro, the dipole moment is equal to the polarizability polarizability, not polarization, times the applied electric field. But I'm not thinking about the micro here, I'm thinking about the macro. That's what we're going to be talking about. Okay, so let's just ignore that for now. So I said the material most of the time polarizes linearly, but not all the time. If you have very intense electric fields, or some unique material that has a very high chi, well, a nonlinear chi, you can get a nonlinear response. So to account for nonlinear responses, you expand the polarization and a power series of the electric field. So, I mean, this is just actually the general polarization. For a general polarization that includes linear and nonlinear terms, you expand the polarization into a first order polarization plus a second order polarization plus a third order polarization. And the right hand side, where the chi's and electric fields are probably just what you think. The universal constant stays the same. Chi 1 is a first order susceptibility times just the electric field to the first power. So that's the linear term. Nonlinear terms go as chi 2 second order nonlinear susceptibility times the electric field squared. So this term depends on the electric field squared. And we can continue, got chi 3 electric field cubed plus so on and so forth. Oh, I should have drawn, I should have did plus on the polarizations here, plus dot dot dot. Okay, so I already said what these are. This P1 is the linear polarization. Chi 1 is the linear susceptibility. P2 is the nonlinear, is the second order nonlinear polarization. Chi 2 is the second order, well, I think that's how you would say it. Second order nonlinear susceptibility. So, for linear, you got P1 equals epsilon naught chi 1 times E. For this might be called the first order nonlinear. But the first one is P2 epsilon naught chi 2 electric field squared. Okay? And keep doing that. Now, the linear response is sort of the most obvious thing. And usually the higher order polarizations, they get smaller and smaller and smaller. And indeed, for this expansion to be valid, the higher order terms must get smaller and smaller. So usually, chi 2 is much smaller than chi 1. Chi 3 is much smaller than chi 2, much, much smaller than chi 1. So on and so forth. So the series has to converge for this to be valid. Now, usually we know everything about our electric field. We know, well, okay, let's start talking about light now. So, our E field varies. If we're speaking about light. because it's electromagnetic wave. So in an electromagnetic wave, the E field varies sinusoidally. And this is time, this axis is time, this is the electric field amplitude. So at time t0, if this is t0, we start at 1, and a cosine wave describes the electric field variation with time, also in space. So we can write our electric field as some amplitude term, E naught, plus cosine of some momentum vector times the position in space, x, minus a frequency times time. And that's really just the general solution for the wave equation, or just in general describes a wave that propagates through space and time. And this E naught is the amplitude at time 0. For this example, I said it's 1. Okay, so the electric field is actually made up of many, many frequencies. So we can think of the electric field as a sum of terms with different momentum vectors and frequencies. So if it's monochromatic, it's just the amplitude at the first frequency times cosine k1x minus omega 1t plus E2 for the second frequency, cosine k2x minus omega 2t plus so on and so forth. Or in other words, you just get your electric field by summing over all the frequencies. So EI naught times cosine k1x minus w omega 1t. But you can also write this as a complex exponential, which is most often done in textbooks because it's easy to take the derivative and the integrals of exponentials. And it's easier to work with exponential identities than trig identities. So usually you'll just see this written as, now the amplitude's a little bit different because it's divided by 2, but it's a constant either way. So you'll see e to the negative I kix plus omega I t plus the complex conjugate part. Complex conjugate part includes the complex amplitude. Okay, so that would be your total E field. So now, how do we sort of find out more about the polarization, find the susceptibility for a certain material and things of that sort? Well, first off, we have to write our electric field like this. So we're looking for the polarization. We want to solve for any higher order polarization, and we want to solve for any higher order chi and the electric field to the ith power. So what we have to do is solve the actual physical situation is represented by a driven, damped harmonic oscillator. And I discussed that in a previous video. So the driven, damped harmonic oscillator is described by the equation x dot dot, which it stands for the acceleration, plus a gamma x dot plus an omega squared x equals a driving term, and here that driving term is E over m times the electric field. So this equation is derived from simply F equals ma, where we're considering a sum of forces, and we're actually dividing all the forces by m. So this term is represented by this term represents the acceleration. So the dots here represent a time derivative, and the x's are functions of time. The electric field is also a function of time. So you can open up your differential equations book and find the solution for this. I'll discuss it shortly. Now this term is this is the damping force. And the damping force is proportional to the velocity of the material, and it's sort of like if you're driving a car, as you drive faster and faster and faster, well, the wind is putting more and more of a force on your car. So that's why it's proportional to the velocity. And the gamma is just a damping coefficient. And the omega is actually the spring constant, is the square root of the spring constant divided by m. The damping constant also depends on the mass. But this term just comes from Hooke's law. That's the restoring force. And this term is the electrostatic force, and comes from Coulomb's law. So that's how you get this driven damped harmonic oscillator equation out of F equals ma. And so if we want to find higher order polarizations, we actually need to include another term, which is an anharmonic term, or terms, and those other terms are represented by some anharmonic coefficient a times x squared. Since it's anharmonic, it depends on the position squared. And higher order terms, you could do bx cubed, so on and so forth. I'm not going to go that high though. Okay, so what do we do when we want to find our higher order polarizations? So to do that, we use a combination of solving the driven damped harmonic oscillator and using perturbation theory. So let me write that down. To solve for PI's okay, I'm going to call this equation 1. Solve x in equation 1 and use perturbation theory. So the perturbation theory part says that we expand our position into higher order terms, and we multiply by a small constant lambda. So lambda times a first order perturbation times lambda squared times a second order perturbation plus lambda cubed times the third order perturbation, so on and so forth. And we also multiply the right-hand side of equation 1. So I'm going to rewrite equation 1 with the antiharmonic terms here. That's equation 1 with the antiharmonic terms. So we also multiply this side by lambda for the perturbation theory part. Okay, and we see that, so let's just take the position as up to the third order perturbation. I'm going to continue this part in the next video. So thanks for watching this part. Have a great day.